Okay, so welcome to today's seminar. So today we have a talk about Higgs measurements from the CMS experiment. The speaker is Jonathan. So Jonathan did his PhD in 21 at Imperial College, and he worked on Higgs bosons measurements in the diphoton decay. And since 21, after graduating, he got first a Schmidt AI Science Fellowship at Imperial, and since 24, he is now a postdoc at Imperial College Fellowship. So he's from 22 to 24, he was the Higgs combination convener of CMS, so we will get the information he presents today from first hands. And the technical contributions to CMS were developments in the fitting and combination software, and he also contributed to the high granularity calorimeter upgrade, and he worked on electron and photon ID in the trigger. And he also was very active in the LHC working group. It's your floor.
Okay, thank you very much. Yeah, thanks for the introduction, and thanks for everyone who's come along and those on Zoom. It's a great pleasure for me to be able to present these new combined measurements and interpretations of the Higgs boson production and decay in CMS. So this is the legacy run-2 Higgs boson combination based on 138 inverse femtobonds of PP collision data at 13 TeV. It really is hot off the press, so the archive link went live at around 4 a.m. this morning. And this is a follow-up to a preliminary result that we released for Morion 25. In terms of where does it sit with previous measurements, so you can think of this combination as an evolution of the nature combination, which we released in 2022 to celebrate 10 years since the Higgs boson discovery. Except now we have new and updated input analyses, many more measurements and interpretations of the data, including, for the first time, a combined SDXS measurement from CMS. In this seminar, I'll begin by introducing precision Higgs boson measurements at CMS, and then go on to briefly describe the input analyses and the methodology we use to combine them. The bulk of the seminar will then be going over the different results, so our measurements of signal strengths and cross-sections, followed up by interpretations in the Kappa framework, in specific UV complete models, and with standard model effective field theory. And all the results that you see through the slides and in the paper are tabulated in the HEP data record, which the link will go live in the coming days. So I'm sure everyone in the room is familiar with the content on this slide, but just to set the scene, in the standard model we have this scalar spin-knot Higgs field which undergoes a process called electroweak symmetry breaking, through which we explain how the W and Z bosons acquire their mass. Through a separate set of interactions, we can, known as the Yukawa interactions, we can explain the masses of the fermions. And after electroweak symmetry breaking, the remaining degrees of freedom manifest as this massive scalar boson, which we identify as the standard model Higgs boson. Such that in the standard model, the couplings between this particle and the W and Z bosons, and with the fermions, are proportional to their mass. So this does a great job at explaining the physics that we see at the LHC, yet we know that there are a number of fundamental questions which remain unanswered. And what I want you to take from this slide is that the Higgs boson really does lie at the center of many of these questions. From the hierarchy problem to defining all flavor structure via the Yukawa interactions, potentially offering a means for to describe the matter-antimatter asymmetry via electroweak baryogenesis, and even potentially providing a portal to a dark sector, it's really key that we make precise measurements of this particle to probe our most fundamental questions. The first port of call is the Higgs boson mass. So the Higgs boson mass is the only free parameter of the standard model Higgs sector. By this I mean that its value isn't predicted in the standard model. So we need to precisely measure the value in order to pin down the Higgs sector. The result that I'm showing here is a combination of the 2016 diphoton and 4-lepton analyses, which measure a value at, measure a value of 125.38 GeV with an uncertainty of around 140 MeV. This is the value that we use for the combination measurements, which I'll show on the rest of the slides. But essentially, by measuring the Higgs mass, we can fix the couplings to the other standard model particles and then have precise predictions for the different production and decay rates. So that's what you see on this slide. The Feynman diagrams at the top are for the different Higgs boson production modes. The dominant channel, the dominant mode is gluon fusion. This diagram in the top left, and that contributes around 90% of the total Higgs boson production rate. The lesser production modes then in order of decreasing cross-section are VBF production, VH production, GGZH and TTH, and then finally the TH contributing diagrams. And what the key thing here to take is that if you look at the Feynman diagrams, you'll see that these lesser production modes have additional particles in the final states. And it's via tagging on these additional particles that we can isolate events of these different production modes and measure them separately. Onto the Higgs boson decays. So the Higgs boson decays directly to vector bosons and to fermions, but also to pairs of photons and Z gammas via loop diagrams. The dominant decay channel, as you see from the table at the top right, in the standard model is Higgs to BB, which makes up around 60% of all Higgs boson decays. But this isn't to say that this is the most sensitive channel, because we need to also consider things like the signal to background ratio and the experimental resolution. So with each of these numbers, you'll see an accompanying uncertainty, and what you'll notice is that, in general, these uncertainties are very small. And that's thanks to work from the theory community over the last decades to really understand these interactions and their associated kinematics. And this is then what we need, these precise references, to be able to compare to our experimental measurements and look for deviations from standard model theory. So what do the experimental measurements of Higgs boson production and decay look like at CMS? So CMS, as I'm sure you're all aware, is this general purpose detector that sits at 0.5, which has different layers of different subdetector technologies interleaved with a solenoidal magnet. And each of these different subdetector technologies becomes relevant for the different Higgs boson processes that we measure. So for example, in the diphoton final state, the key subdetector here is the CMS eCal, where we benefit from the excellent energy resolution of the eCal to provide a sharp peak in the diphoton invariant mass spectrum above the smoothly falling background. It's a similar story in the Higgs to 4 lepton channel. So we require the eCal for the energy measurement of the electrons, along with the silicon tracker and the muon chambers, again, to provide this really sharp peak above the background from which we can measure Higgs boson events. For Higgs to BB, then, on the other side of the coin, the signature is a lot more messy. And for this, we require sophisticated machine learning techniques to be able to identify jets that come from the hadronizations of B quarks. Where do we sit then in the timeline since discovery? So the Higgs boson was discovered back in 2012, and at this point, we'd created around 200,000 Higgs bosons within the CMS detector. Fast forward to the end of 2018, the end of run 2, we had produced around an order of magnitude increase, so around 7.7 million Higgs bosons. We're now approaching the end of run 3. This corresponds to 24 million Higgs bosons produced at CMS. And then looking forward to the end of the high Lumi LHC period, we'll again get this order of magnitude increase in the number of Higgs bosons produced. So really, we're only at the beginning of this journey into understanding the Higgs boson. But what I want to demonstrate from this seminar is really the scientific reach that we've been able to achieve with just 5% of the total LHC data set, and demonstrate how far we've come from discovery. So what did run 2 Higgs boson measurements look like? So I think this is a nice illustration comparing the Higgs to 4 lepton peak at discovery to what we obtained at the end of run 2, showing that during this time we were really able to enter the era of precision measurements in the Higgs sector. It wasn't just the increase in statistics, though. We accompanied this by advancing our analysis techniques, using sophisticated machine learning algorithms to essentially squeeze every drop of information from the data. The large data set also enabled us to move beyond inclusive measurements and start to measure the kinematics of Higgs boson events, which by comparing to the theory provides this new handle on BSM physics. The measurements that go into the combination that I'll speak about make these measurements in the simplified template cross-section framework. So for those of you in the room who aren't aware what this is, essentially we split Higgs boson production into the different production processes, and then events from these processes are partitioned into these non-overlapping kinematic regions of phase space, which we refer to as SDXS bins. These partitions are made in kinematic quantities such as the number of jets or the transverse momentum of the Higgs boson. And they're designed to firstly isolate regions of phase space which are particularly sensitive to BSM, for example, at high transverse momentum, but also to reduce the theory dependence in our measurements and avoid large extrapolations by aligning with the experimental acceptance. An analysis then targets these measurements by designing analysis categories to be pure in events from a given SDXS region so that it can unfold the cross-section and build up these granular maps of Higgs boson production at the LHC. Sorry. Okay, so then onto the combination. So this is a nice diagram that we produced for the public briefing to accompany the preliminary results last year. And what you see here are the different decay channels which enter our combination. So we have the fermionic decay channels on the left. That's sorry, this is a bit funny. There we go. The Higgs to mu mu, Higgs to tau tau, and Higgs to BB channels. And then the bosonic decay channels are made up of Higgs to gamma gamma, Higgs to ZZ, Higgs to WW, and Higgs to Z gamma. The 5 in the middle, we all have observations of these decay channels, so with greater than 5 sigma sensitivity, whereas the ones on the outside, we're at the evidence stage. So these are what we refer to as the rarer decay channels. What's nice then is to look at the mass distributions for each of these channels. These are with the background subtracted, except for the 4-lepton state. And I think what these plots show is this kind of trade-off that we have in the different channels from the large branching fraction providing a larger yield, but then also balancing that with the signal-to-background ratio and the experimental resolution. And it's by then combining these channels that we can provide the ultimate precision to Higgs boson measurements. The table on the slide here lists all of the different input analyses which go into this legacy run-2 combination, where those highlighted by the blue stars are the new and updated input analyses since the nature combination. This is such that all inputs now are based on the full 138 inverse femtobonds of data. And what you can see by the third column in this table is that in each of these channels, we target multiple production modes in the measurements. For a number of specific interpretations, which I'll discuss later on in the slides, we include dedicated searches for Higgs to invisible final states and off-shell Higgs production measurements. And the other thing I wanted to say is that throughout Run 2, CMS have provided these excellent analyses searching for Higgs to charm-charm, but they're not yet included in this combination because in Run 2, the analyses were not statistically orthogonal with the Higgs to BB analyses. And then the orange stars are just indicating which measurements in this list are targeting the kinematic regions defined by the SDXS. Okay, so then how do we extract the Higgs boson properties from the data? So an analysis will select the events and categorize them into analysis regions. And then for each analysis region, we define a likelihood, which basically tells us the likelihood to observe a given data set given some model. This model is made up of our parameters of interest, alpha, such as the Higgs boson cross-sections, i.e. what we're trying to measure, and the nuisance parameters, theta, which represent different sources of systematic uncertainty in the measurement. The model itself consists of both a signal and a background component, where what I want to stress is that the signal models are constructed separately from events from each of these SDXS regions so that we can unfold the kinematic cross-sections. Sorry. The signal yield parameterization then is given by the formula that you see on this slide. This is just the product of the theory predictions on the cross-section and branching fraction, your efficiency times acceptance, and your luminosity. But the key quantity which is relevant for these measurements are these signal rate modifiers, which essentially tell you how a given process in a given decay channel scales as a function of the parameters of interest. And then by injecting this into the likelihood, we can extract our information on alpha. In the legacy run-2 combination, we fit many models to the data, as listed by the table here. So what the table is showing is all of the different interpretations we have. The first column gives the number of parameters of interest, and then the subsequent columns show you which analyses are included in that particular interpretation. And altogether, this represents the most comprehensive study of the Higgs boson production and decay from CMS to date. Okay, so how do we combine these? Well, we do this by taking the product of the likelihoods in each analysis region times by this constraint term on the nuisance parameters, which in this form looks quite simple, but in reality, there's a lot of complexity hidden in this equation. So in the combination, we include 1,048 different analysis regions and have over 10,000 nuisance parameters representing these different sources of systematic uncertainty in our measurement, where the kind of interesting task in any combination is understanding how these sources of systematic uncertainty, both from theory and experiment, are correlated across the input analyses and defined by a single parameter in the likelihood. We extract then our measurements by defining a profile likelihood ratio test statistic to get the best fit values and the confidence intervals on our parameters of interest. And fitting this test statistic requires a highly optimized software. For this, we benefit from the developments to the CMS combined tool over recent years, which have really made this combination possible. In addition, we perform these pruning strategies to reduce the complexity of the statistical model somewhat. But even so, it's still a huge technical challenge to extract the combination results, requiring a massive computational demand. And what I'll then show for the rest of the seminar, I hope to convince you that it's worth the effort. So already onto the results. The first set of results that I'll show are the signal strengths. So in the signal strength formalism, we introduce these parameters which scale the rate of Higgs boson production and decay relative to the standard model predictions, such that the uncertainties in these predictions are folded into our measurement. We fit these at different levels of granularity, and the first is the inclusive measurement. So we have just a single parameter which scales all Higgs boson processes equally. And what we obtain is a value of 1.014 times the standard model prediction with an uncertainty of around plus or minus 5%. Now, while this is a terrific achievement, what I want to highlight on this slide is the fact that this 5% is almost completely dominated by the theoretical uncertainty, so the standard model prediction here. And a lot of work is needed to be able to bring this down to the excellent precision that we have on the experimental side. We can then relax the model and introduce a separate signal strength modifier for each production mode. So that's what you see by the 6 parameters below this line here. So we measure gluon fusion, VBF, WH, ZH, TTH, and TH production separately. The plot is showing essentially the best fit points in the white circles, your confidence intervals at 68% and 95%, where the 68% are then decomposed into the statistical uncertainty, the experimental systematic, and the theoretical systematic in blue, orange, and purple, respectively. The uncertainties are getting really small on these measurements, so ranging from around 8% to up to 25% for these 5 production modes that you see above. And then when we look at the rare production mode, TH, what we find is an uncertainty of around 50% with respect to the best fit value. And this is interesting because, in fact, what we measure here is an upwards fluctuation from the standard model of around 2.2 standard deviations. I again just want to highlight the contribution from the theory uncertainties when looking at the gluon fusion parameter. So many people in the room will be familiar with this plot on the top right, which shows the theory uncertainty budget as a function of the collider energy, where I've added this red dashed line to indicate 13 TeV. And what's nice to see over recent years is these developments on the theory side that have managed to bring down these uncertainties, and in some case all the way down to 0. But even so, what I highlight in this red box are the updated values, and you can see that even there, we're still going to be dominated by the theory uncertainties when it comes to this measurement. We also perform a separate measurement considering a signal strength modifier per decay channel. So you have your bosonic decay channels, and followed by the fermionic decay channels, and then at the bottom, looking at the rarer decay channels, Higgs to mu mu and Higgs to Z gamma. So Higgs to mu mu is now measured with an uncertainty of around 40%, and Higgs to Z gamma around 100%, where, in fact, in the Z gamma decay rate, we see this upwards fluctuation at around 1 to 2 standard deviations above the standard model. We can break down these uncertainties further into the contributions from the different sources. So that's what the plot on the right is showing. So for each of these parameters, the red boxes are the total uncertainty relative to the best fit values. And then the blue box, the purple box, and the orange box are the contributions from the statistical component, the theory systematic, and the experimental systematic. We then break down, for those of you with keen eyes, you might be able to see, we break down these the experimental and theoretical further into the different sources to give an idea on kind of which uncertainty sources are contributing to which measurements. So looking at the inclusive, we've already highlighted the fact that this is now becoming dominated by the theory uncertainty, which you see by the purple band. I think another interesting thing to look at is how the experimental uncertainties are kind of equally shared amongst the different sources. And what this means is that to reduce the experimental uncertainty, we're going to have to kind of target all areas of our measurement in the future. Then looking at the per production mode and per decay channel, we find that the different channels are dominated by different sources. Take, for example, the Higgs to diphoton decay channel, and looking at the experimental uncertainties, you can see, as expected, the uncertainties on our photon measurements are dominating there. But anyway, the key takeaway from this slide is that at this level of granularity, we see for a lot of these parameters, the systematic uncertainties are becoming dominant above the statistical. Okay, so then we can relax the assumptions further and introduce a separate signal strength modifier per production times decay channel. So that's the results that you see highlighted by the red box on this slide, where along the columns correspond to the different production modes and the rows the different decay channels. So each is accompanied by a measurement. You have your best fit values and your 68% confidence intervals, where the orange lines are the systematic components of these uncertainties. And these are then compared to the standard model prediction at 1 in the red line, and then the blue lines are the combined measurement that we make across the different decay channels. I really like this plot because I think it gives you this global view of Higgs boson and production and decay measurements at CMS. And what's nice to see is how the different decay channels contribute in terms of sensitivity to the different production modes. So take gluon fusion, for example. What we see here is the measurement is dominated by the bosonic decay channels, whereas then when we look at VBF, we see tau-tau is the most sensitive channel. And for VH, for WH, ZH, and TTH production, we see here Higgs to BB as the most sensitive channel, where we can balance this large branching fraction with the fact that we have additional particles in the final state to tag on and reduce our backgrounds. At this point, I should say that with all our results, we also provide the correlations between the measured parameters, which is, of course, crucial for future reinterpretations. Now moving on to cross-sections. So the key difference here is that the theory uncertainties affecting the normalizations of the measured parameters are removed from the fit and are instead attributed to the standard model predictions. So what you see by the plot on the right is the standard model predictions along with their associated uncertainties for each of the different kinematic regions, these SDXS bins, for which our combination is sensitive to. By designing the likelihood in such a way that our signal models are constructed separately from events from each of these regions, we can then unfold the cross-sections and obtain the measurements that you see now on this slide. So what the plot is showing are the best fit values and the confidence intervals for each of these SDXS bins, where the larger, kind of wider boxes are the systematic components of the uncertainties. And at this level of granularity, we see that the statistical uncertainties dominate. We measure 13 cross-sections related to gluon fusion production, 5 for QQH production, 4 for both WH leptonic and ZH leptonic production, 5 for TTH production, and then 1 inclusive TH measurement. The uncertainties range from around 14% for the highest cross-section bin to up to 260% for this rare, extremely high PT region for gluon-gluon fusion production. Then comparing to the standard model, we provide this ratio panel, and you can see across the board that the measurements show good agreement with the standard model. However, there are a few interesting deviations. So one I want to highlight is in the VH leptonic channels, where we see this consistent excess above the standard model predictions for both WH leptonic and ZH leptonic production. Just like in the signal strength production mode measurements, we also then obtain this excess also in TH production in this particular model. So these cross-sections are fit together with ratios of branching fractions, which allows for BSM modifications in the Higgs boson decay rates. But all in all, this result represents the first ever combined SDXS measurement from CMS. We then go one step further and perform an additional fit where we introduce a separate parameter per SDXS bin in each decay channel, where each channel is fit at the granularity used in their respective publications. In the end, this defines a fit with 97 parameters of interest. So we're fitting this all with a single likelihood, which constitutes the most granular fit ever performed by CMS in the Higgs sector. At this point then, I'll go on to talk about interpretations of the data, so where we replace these kind of rate modifiers by scaling terms, which are functions of the parameters of interest. And we'll start with discussing the Kappa framework. I'm sure a lot of people in the room are familiar with the Kappa framework. This is where we introduce these leading order coupling modifiers to act as essentially multiplicative constants to scale the Higgs boson couplings to standard model particles. The scaling terms then become functions of the kappas, where we employ the narrow width approximation to separate the effects at production from the effects at decay. And you can see from the table at the bottom left of this slide how the different production modes and decay channels depend on these kappas. The first fit I'll discuss is in the so-called resolved configuration, where the loop diagrams are resolved into their standard model contributions. And in this configuration, we fit 6 parameters, and the results of which you can see in the bottom right of the slide. So our couplings to vector bosons are measured with uncertainties of around 5%. Then for the third generation fermions, kappa T, kappa B, and kappa tau, we measure with uncertainties ranging from 6 to 12%. And then for the second generation fermion, the muon, with a much lighter mass, we're still able to measure this coupling with around a 20% uncertainty. What's new since the preliminary result is that actually we've expanded this interpretation to look at the sensitivity to the signs of these couplings. So this sensitivity comes when we consider the interference between diagrams, which then leads to these terms in the scaling functions which depend on single powers of the kappas. So in this resolved configuration, we're sensitive to the relative sign of kappa T, kappa B, kappa W, and kappa Z. These are relative signs, so we fix one to be positive, kappa T, and then consider negative values for the other kappas, and the results of which you can see highlighted by these orange circles. So to talk through them, in kappa B, our sensitivity here comes just from the gluon fusion production rate. This is a weak interference term, so the sensitivity isn't great, and we're unable to exclude negative values at the 68% confidence interval. For kappa Z, our sensitivity is slightly better. This comes from the GGZH production rate, and here we exclude values beyond the 68%, but we're still unable to exclude negative values at the 95% confidence interval. And then for kappa W, what we find is actually the precise measurement of the Higgs to gamma-gamma decay rate means that we can reject the negative values of kappa W easily at the 95% confidence interval. You'll be more familiar with the plot shown in this format. So this is showing the couplings as a function of the particle mass, where we have this kind of striking confirmation of the standard model theory, this linear dependence across 3 orders of magnitude in the mass. Before then going on to discuss more interpretations, I just want to highlight 2 points for this plot. The first being a measurement of the Charmu-Kawa. So as I said a few slides back, there's been a lot of work at CMS to be able to pin down this coupling, this hard-to-measure coupling, and we provide an additional plot which essentially just overlays the constraint we have from a VH plus TTHCC combination, where we find again that the coupling, at least within the uncertainties, agrees with the standard model prediction. The other point is then looking at the higher side of the plot, the higher mass scales. We need to work out how the Higgs interacts with itself. So the standard way to do this is with di-Higgs production, yet we do have a means for probing this in single Higgs production, and this comes from next to leading order electroweak corrections to the single Higgs production rates. I don't have time to go through this in the seminar, but I have included the results for this in the backup. Okay, so we've measured these kappas, these kappas. We've managed to constrain the couplings. What does this mean? What can we say in terms of constraints on BSM theories? Well, when we consider extended Higgs sector scenarios, we find that these tend to modify couplings for up-type versus down-type fermions separately. So we probe another model where we introduce these common coupling modifiers, kappa U, kappa D, and kappa V, which are common for up-type fermions, down-type fermions, and the vector bosons, and then probe the specific BSM scenarios by floating the ratios of these coupling modifiers. So these are the results that you see on this slide, where I'm highlighting the parameter which is relative to these separate modification of the up-type versus down-type quarks. Down-type fermions, sorry. And what you see in this parameter is that we see good agreement with the standard model with small uncertainties. So we can use these then to exclude parameter space for specific UV extensions of the standard model. And that's what I'll show here. So again, this is a new interpretations that we've added since the preliminary result, where we look at using the results on the previous slide to constraining the parameter space of specific UV completions. And what I'll go through is an example in the HMSSM. So this is a minimal supersymmetric extension of the standard model where we introduce a second Higgs doublet into the standard model, which after electroweak symmetry breaking yields these 5 physical scalar bosons. So you have your 2 CP even states, little h and big H, your CP odd state A, and then your charged Higgs. We can assume CP conservation in a discrete Z2 symmetry, which then leads with 4 2HDM scenarios, the type 1, type 2, lepton-specific, and flit. And the constraints on these kind of generic models are included in the backup slides. What I'll talk about then is the HMSSM, which is a specific type of the type 2 extension, which introduces this additional non-trivial fermion-boson symmetry to fix the mass relations between these bosons. When we do this, we find that the Higgs couplings, as you can see by the table on the right, are dependent on only 2 free parameters of the theory. That's the mass of this pseudoscalar A and tangent beta, which corresponds to the ratio of the vacuum expectation values for the 2 Higgs doublets. Okay, so then what we can do is essentially use the parameters on the previous slides and define them as functions of MA and tangent beta, which are what these plots are showing. So in your MA versus tangent beta plane, you can traverse this plane and calculate the value of these ratios of coupling modifiers, which is shown by the color scale, where these lines are kind of contours of constant value of lambda du. What we find is that the couplings go asymptotically towards the standard model for high values of MA. But anyway, what we do then is take the test statistic as a function of these 3 parameters and use these relations to project this onto the MA versus tangent beta plane to place constraints on the specific UV extension of the standard model. So these are the constraints on the HMSSM, where we're able to exclude MA values up to around 600 to 650 GeV, depending on the value of tangent beta. What becomes interesting then is when we compare these constraints to what we obtain with direct searches for new physics, which is what you see in this plot. So the constraints from this combination are shown in this light blue color here, and you can see that there is this region of parameter space where the indirect constraints from the Higgs boson combination provides a unique sensitivity within tangent beta between 2 and 7. So then coming back to the kappa framework, but with a bit more of a kind of BSM hat on, we define a separate model which introduces these effective coupling modifiers to introduce new physics into the GGH production loop and the Higgs to gamma gamma and Higgs to Z gamma loop diagrams. These are kappa G, kappa gamma, and kappa Z gamma. And the first model that we fit, the results of which you can see on the right, assume no additional decays to BSM particles. So what we obtain, so these three parameters at the bottom are our effective coupling modifiers. We see that kappa G and kappa gamma show good agreement with the standard model, yet we observe a slight excess in kappa Z gamma, which is consistent with this excess we saw in the Higgs to Z gamma decay rate. When we consider the signs of these couplings, in this model we actually prefer a negative value for kappa W. So where does this come from? Well, when you look at the TH production scaling functions, you'll see that there are these interference terms which, if kappa W has a negative sign with respect to kappa T, then it would cause a large enhancement in these cross-sections, which then matches what we see in the data with this excess in TH production. So this is why we favor negative values, and to be clear, the difference with respect to the resolve model here is that we don't get these interference terms entering the Higgs to gamma gamma decay rate, because here this scales just as kappa gamma squared. We extend this model to allow Higgs boson decays to BSM particles by introducing these two parameters. So branching fraction to invisible final states, such as potential dark matter candidates, and to undetected final states, which are basically made up from either exotic topologies that we don't probe, or modifications to the standard model final states that are not included in the combination, such as Higgs to CC. The first parameter is constrained by directly adding these dedicated searches for Higgs to invisible decays into the combined likelihood. This is an example from the VBF Higgs to invisible analysis, which targets Higgs boson events with large missing energy. And what we obtain in terms of the branching fractions are constraints of less than 13% and 21% respectively at the 95% confidence interval. There is a caveat which comes with this model, which is that we require an external constraint on the coupling modifiers to kappa W and kappa Z, such that their absolute value has to be less than 1. The reason we do this is that it avoids a complete degeneracy in the total width, where you can account for a non-zero undetected branching fraction simply by scaling all of the kappas up equally. So it's a well-motivated choice. This particular constraint is satisfied for a wide class of BSM models. But even so, it's still injecting this kind of model dependence into this particular fit. So we asked ourselves, can we alleviate this model assumption by introducing some new measurements into the combination? And the answer lies in off-shell Higgs boson production. So we included off-shell Higgs to 4-lepton analysis regions into the combination for the first time, where I'm showing one of these analysis regions on the right-hand side of this plot, targeting events with a 4-lepton invariant mass greater than 220 GeV. The key thing here is that we're able to leverage the different scaling behaviors of on-shell versus off-shell production, where, if you notice, the terms in this equation here for off-shell production don't depend on the total decay width. So essentially, we can use this information in the fit to directly constrain the total Higgs boson decay width directly from data. This is the third model we fit then, which you can see the results in purple on the plot on the right. And the key thing here is that we've managed to alleviate this external constraint that we placed on the kappa V parameters and still obtain a constraint on the greater than 1 side. All right, so that brings me then to the final interpretation that I'll show today in the standard model effective field theory. So I spoke a bit about how we can extract constraints on a specific UV extension, namely the HMSSM, but of course there are a number of different models to probe. And what we want then is a framework that we can kind of do this in an agnostic way to scan over the full potential space of BSM theories. The answer then lies in standard model effective field theory. So this is where we assume no, given the fact that we've not observed any new states in our data, we assume that the new physics exists at a mass scale beyond the reach of the LHC. So lambda being the mass scale, you can see here an example illustration that the new physics is beyond the reach, and then we use the EFT to effectively encode the imprints on the standard model processes and on their distributions. The mathematical formulation is shown here. It's essentially an extension of the standard model Lagrangian, where these terms come with increasing orders of mass scale suppression. They introduce higher dimensional operators between the standard model fields, which essentially take the short distance, high energy new physics interactions, run these down to the energy scale at the LHC, and replace them with contact interactions between the standard model fields. And it's these contact interactions that we then parameterize by the so-called Wilson coefficients of the theory, such that our task is to use the Higgs boson production and decay rates to constrain these Wilson coefficients, where any significant deviations from zero would be a smoking gun for new physics. Before going on to the results, I just want to stress the importance of differential measurements here. So one of the drawbacks of the Kappa framework is that it only considers modification to the total rates of production and decay, which means that we need extremely high precision to be able to probe physics at a given mass scale. When we look differentially, what we find is that modifications to the spectra scale like Q over lambda squared, where Q is the momentum transfer in the process, such that we need less sensitivity here to be able to probe new physics states at the same mass scale. This is where SDXS measurements come in, so that we can use the kinematic information which is available in these SDXS measurements to enhance our sensitivity to beyond the standard model physics. So what we need to do is parameterize the Higgs boson production and decay rates in terms of the Smeth-Wilson coefficients. And we do this at the granularity of the SDXS binning scheme exactly to do this, to incorporate this kinematic information in our measurements. Just like the Kappa framework, we use the narrow width approximation to tell us that our scaling functions can be split up into the effects at production, Higgs boson production, and at decay. And in this particular interpretation, we're only considering the dimension 6 operators, which extend the standard model Lagrangian, because the odd dimension violate B minus L conservation, and any higher dimensions are suppressed by increasing orders of 1 over lambda squared. This still leaves an extremely large parameter set, so we need to impose some constraints to be able to reduce this to a manageable level. We introduce a flavor symmetry, top U3L, where we have separate operators for the heavy quarks, T and B, and for the light quarks, U, D, S, and C, and then a separate set of operators which are common for all lepton flavors. In addition, we assume we only consider CP conserving operators because of the lack of information in our SDXS measurement, which can separate CP conserving from CP violating effects. And in total, this brings the total operator set down to 129, of which this combination is sensitive to the 43 operators, which you see in the table on the right-hand side. When we consider only a single insertion of new physics into each diagram, like you see on the right, our scaling functions become quadratic formula in terms of the Wilson coefficients. So what we need to do, our task is then to derive these A and B prefactors, which define the linear and quadratic terms, to be able to understand how these Wilson coefficients impact our SDXS measurement. The analytic solutions are used for the Higgs to gamma gamma and Higgs to Z gamma decays, which are defined at next leading order in electroweak theory for the SMEFT. Whereas for all of the processes, we use Monte Carlo simulation, where we generate the standard model events and then inject the new physics vertices to understand how the rates change as a function of these Wilson coefficients. So in the end, we obtain the parameterization that you see on this slide. There's a lot of information here, so I'll go through it slowly. But along the x-axis, you have the different SDXS bins, along with, on the far right, the different branching fractions to the decay channels that we consider. And then each of these rows is essentially showing how these observables change when you turn on different Wilson coefficients. So just to pick out an example for CHG, we saw a few slides back how this introduces a contact interaction between the gluons and the Higgs. You can see that by turning on this operator, we get a shift in our gluon fusion SDXS bins, which is kind of flat until we go to very high transverse momentum, where we get this increased effect as a function of CHG. The first set of results that we provide are these so-called one-at-a-time constraints. So this is where we consider just new physics in one Wilson coefficient at a time while fixing the others to the standard model. And we probe this in two models, both the linear parameterization, which only extends the scaling terms up to order 1 over lambda squared, and the linear plus quadratic, which goes up to 1 over lambda to the 4, where we can use the difference in these parameterizations to kind of understand how higher order effects would impact our measurements. The results then are shown on the right-hand side of the slide. So again, it's these huge plots, but what it's showing is for each of the Wilson coefficients that we're sensitive to, you can see the best fit values and the 68% and 95% confidence intervals for both the linear and the linear plus quadratic parameterizations. The constraints then are kind of reinterpreted in terms of the upper limit on the mass scales that we can probe, which vary between around 500 GeV up to tens of TeV, depending on the operator. If we look at this panel here, you can see that comparing to the standard model prediction at 0, on the whole, we see good agreement with the standard model, and yet there are a few interesting deviations. The parameter which we see the largest deviation for is in this CHQ3 Wilson coefficient, where we obtain a p-value with respect to the standard model of 0.01. So looking at the effects of this particular operator, we see that by turning the Wilson coefficient on, we get an enhancement in the WH leptonic and ZH leptonic cross-sections, which increases as a function of the transverse momentum of the vector boson. Then when we compare this to our XTXS measurements, we see why we're seeing a deviation in this parameter. So we, as I mentioned a few slides back, we observed this consistent excess in the highest PTV bin for WH leptonic and ZH leptonic, and this is what's essentially pulling this Wilson coefficient away from the standard model. Now, before we get too excited and say this is a sign of new physics, the same deviations aren't present in the equivalent Atlas Run-2 analysis. And recent theory developments suggest that the standard model actually underpredicts in these regions, which would bring the predictions closer to our observed values. That said, I think it's still a very interesting example to show how we can use the SMEF framework to probe these consistent deviations from the standard model in our measurements. The final result then looks at simultaneously constraining multiple Wilson coefficients. This is a tricky task because of the degenerate effects between different operators, leading to flat directions in the likelihood. So what we need to do is perform a principal component analysis to identify which directions, in Wilson coefficient space we're sensitive to. And in the end, we find that we're sensitive to 17 linear combinations of the Wilson coefficients, as you can see by the matrix on the left-hand side of this plot. And then we constrain these in a simultaneous fit and obtain the results that you see on the right. Again, we see good agreement with the standard model across the board, where the largest deviation is in this eigenvector 3, which then if you compare with the matrix on the left, you see the largest contribution comes from this CHQ3 parameter. So it's consistent with the results that I showed on the previous slide. All right, so at that point, I'll stop showing new results and start to wrap up. So I hope I've convinced you with this wide array of measurements and different interpretations that the legacy Run-2 combination really is a stress test of the standard model. It's our most comprehensive study of Higgs boson production and decay from CMS to date. And what we find is the majority of measured parameters are in agreement with the standard model, yet there are a few interesting tensions that we should follow up on with more data. Looking ahead to the future then, I think what's very impressive is that all of this was done with just 5% of the total LHC data set that we'll get by the end of the high Lumi LHC operations. Now, while the breadth of these measurements is large, many of the measurements still have large uncertainties, so there is plenty of parameter space for new physics to be hiding. And to kind of target to bring down this parameter space, CMS are busy analyzing the enormous Run-3 data set, not only benefiting from the large statistics, but also the improved analysis techniques and advancing the measurement frameworks. The high Lumi LHC era then promises percent-level sensitivity to the couplings and will be able to precisely map out the Higgs boson kinematics. So yeah, I just want to conclude on the statement that this is just the beginning. We have a few exciting decades to come in our exploration of the Higgs sector. And with that, I thank you for your attention.
Yeah, thank you very much to present us these comprehensive results. I'm always impressed by these combinations because you don't talk about the real difficulties to deal with the fact that all these analyses do something slightly different over time, and then you have to harmonize all that. So it's quite impressive that the results you achieve. So let's have some questions and comments. Yes, there's one from the outside. Hometown, can you ask your question, please?
Hi, can you hear me?
Yep.
Okay. First of all, congratulations on this achievement. It's really impressive. And also thanks, Jonathan, for this very clear presentation. I really enjoyed it.
Thank you.
So if back to the previous slide, so I think for this coupling versus mass plot, when you overlay the charm you cover coupling strengths with others, they are actually based on different assumptions, right? If you really introduce real freedom into the fit with the proper Higgs to CC constraints, you will see in other strength parameters because you have an additional degree of freedom entering the total width, which is not so well constrained with our current data.
Yeah, you're completely right. The constraint on kappa C here comes with the assumption that all of the other kappas are fixed to the standard model. But it's just an illustrative example to show how this constraint compares to what we obtain in the combination.
Okay, do we have more questions? Maybe I ask one.
Yeah.
So where do we go with run 3? So what is the next challenge somehow?
For the combination side, the challenge will be on the size of the statistical models that we're trying to bring together. Not only because of the increased data set, but as I said here on this slide, we're advancing the measurement frameworks. We're trying to go more granular in the kinematics, which means that the statistical models are going to be absolutely huge. So we need to continue to kind of develop these fitting frameworks, explore perhaps more intense pruning strategies that won't impact the results. Yeah, I hope that by the end we'll have a consistent framework, both between CMS and Atlas, on which we can perform these combinations.
Okay, and in terms of the standard model, Higgs, I mean, you showed that these differential measurements are quite important, and I guess this is where you can improve mostly? Or?
Yeah, right. So the large statistics, the increase in statistics that run 3 allows will allow us to basically bin finer in the kinematics. So you can see in this plot here, we're able to measure 32 different kinematic regions. Okay. By increasing the size of the data set, we can then start to probe more and more bins in this framework, picking out regions that, say, are particularly even more sensitive to BSM physics by binning finer in the transverse momentum.
So we have another question on Zoom. Adrian?
Yes, hello. Yes, thank you very much for this very interesting overview. I do have a question on one of your last slides regarding the EFT basis rotation and the PCA. I understand as an experimentalist in why those directions are in the likelihood are important and how they can help us shape our future analysis. But my question is, do you happen to know in what measure those directions, identifying those directions can be useful for theorists or for theory inputs?
I didn't quite catch that. Could you just maybe summarize the question again? Sorry, I couldn't quite hear.
I'm so sorry. Yeah, my question is, how can this direction, those EV0, EV1, etc., can be useful for theory inputs?
Yeah. So along with these constraints, we also provide the correlations between these parameters. And essentially what we can do then is then use that to specifically UV match to some theory. So say you have some UV complete theory, you bring this down to the LHC energy and interpret what this means in terms of the nominal Smith-Wilson coefficient basis. Then we provide the rotation matrix that you see here, so you can rotate these values into our particular basis and then use the likelihood that we provide to extract constraints on these particular UV theories. So essentially with the constraints, the rotation matrix, and the correlations between these parameters, you can use this to do UV matching to whichever BSM theory is your choice.
Okay, more questions in the room. We didn't have a question in the room yet. Yes, can you say your name, please?
Kerstin from DAISY. Thanks for this very nice, large set of results. I have one question, maybe best asked on slide 18 or around there. So you had commented in general that agreement with the standard model is quite good. The p-values you show, some of them are like 0.03, 0.04, and so on. You had pointed out some areas of phase space where you have certain disagreements. But can you comment a little bit more on, those wouldn't drive, for example, the p-value that you see here. Can you comment a little bit on compatibility between the different channels? I'm sure this is something that you looked into.
Right, yeah, absolutely. Essentially, the p-values are low, but what we found is that the deviations aren't particularly consistent between the different channels. So say, I think this is a nice example. We obtain a really small p-value here, but what we see is like, say, in a particular measurement, gluon fusion at low PT and Higgs tau tau, we see a deviation, but then in the other channels, we don't see this. So these kind of deviations from the standard model aren't particularly consistent, which for one tells you that maybe it's not BSM. And then another thing to say is that at least when you go to this kind of level of kinematic granularity, there's kind of two components to this p-value, right? It's not only on the experimental side, but it's also on the theoretical side. So if we've under-predicted some of the uncertainties on our theory, then also this would lead to a tension with our measurements and bring the p-value down.
Yes, can you please say your name?
Hi, it's Christina from PISA. Thank you for these very nice results and the clear overview. I had a curiosity about the future of our fitting tools. You may know that for the W mass measurement, we have this new fitter, Rabbit, which is optimized for order of Newton's parameters that you've shown. So I was wondering if in the Higgs combination group there's discussion to moving towards this framework and how much work would go into making that possible?
Yeah, so there's been a lot of work within the common analysis tools group that we have at CMS. I think one particularly exciting avenue is to introduce automatic differentiation into the likelihood. So maybe in the WMASS fitting framework, you have this via, is it with the PyTorch library, I think? Or, yeah, right, exactly. Or Tensor, yeah. Whereas here, we're using a new development from Root, which can kind of at compile time, produce the gradients for the likelihood, which should, in principle, speed up the fit. So yeah, there's plenty of work going on in developing, pushing the fitting software, which will hopefully bring us that kind of leap that we need when it comes to doing the combinations at run 3.
Okay, do we have more questions? Yes, can you please come close to a microphone and say your name?
Hi, Heather Gray from Berkeley. This brings me to a question on the sort of technical side. I'm curious, for some of these highly complex fits that you run, how long do they take or how much computational power?
Is that the secrets that I want to spill? Yeah, they're computationally very heavy. Each parameter point, it depends on where you are in parameter space. Because if you're close to what fits the data, then it can be quite quick, but as you move away, then the fit can take longer. The largest runtime would be about 8 hours using 8 CPU cores for a given point in parameter space. And when you consider that, we're, like this model, for example, we have 97 parameters of interest. Each one we have to sample different points across the likelihood scan to get the confidence intervals, then it becomes a huge technical challenge. Yeah.
Okay, we can take one more question. Yes, can you please say your name?
Carsten Königke, Göttingen. Thanks a lot again for this. Just for my own curiosity, you mentioned in the beginning that you use Higgs mass value that is you superseded it about a year and a half ago, and changing that parameter in the likelihood is pretty straightforward, or like the resulting branching fractions from the standard model in cross sections. So why did you choose to stick with the superseded value?
I think, okay. So the statement that changing the value is straightforward is not the case when you consider how it would affect the models that we fit. So for example, for input analyses that have extremely good mass resolution, like the mass, like the diphoton decay channel and the Higgs to 4 lepton decay channel. If those models have been constructed for a particular mass, then it actually requires a lot of surgery to be able to define those models at different values of the Higgs boson mass.
Sure, but I mean, we've all done this in the past, and it was
right.
We know how to do it. That's what I'm saying.
Yeah. So in the end, because of it got to the point of combination, and some of the models were fixed at the value that we use in their publications. We end up choosing 125.38 GeV in this combination. The results aren't particularly sensitive to that MH value because we're measuring production and decay rates here. So they aren't particularly sensitive, but indeed, in the next combination, we'll use whatever the latest value is. Thanks.
Okay, then thank you again for this nice seminar.
Thank you.